Hey, we have here a pretty interesting looking integral. We've got the integral from 0 to pi over 2 of sine squared x over sine squared x plus cosine squared x dx. So there's a couple of obvious things that are jumping out. Now, first of all, sine squared x plus cosine squared x, this is just 1. So I could actually very quickly reduce this to sine squared x. Then we could use the power reduction and write that as 1 half minus 1 half cosine 2x, integrate and be done. That's not bad, but the other thing I really wanted to notice is this is actually also in the form of King's principle. You notice for King's principle, the most typical case we see is a sine, cosine, sine, or cosine in the numerator, and then we have the same exponent. Regardless of what the exponent is, it just happens to be squared here. Because we're using King's principle, this actually could be easier because you could basically skip to a solution. I'm going to do the steps, so maybe it's a little longer this way, but all good. Let's just do it. So I'm going to make my u substitution. Adding our bounds together, we're going to have pi over 2 plus 0 is pi over 2 minus x. And I can solve for x, so we'll see that x is going to be pi over 2 minus u. Take a derivative, and we're going to have dx equals minus du. And then we'll do this substitution. When I plug pi over 2 in for our x, we're going to have 0 for the upper bound. The lower bound is going to become pi over 2. And then in the numerator, our sine squared, we'll plug in, let's see, for x, we'll plug in this pi over 2 minus u. And then we'll do the same in the denominator here. Sorry, my handwriting's getting kind of messy. And do it on the cosine term. And then we're going to have our minus du. Now what I can do is take my minus here, and we'll just use to swap the bounds. So we can bring it up front, and we can swap it back to what we had originally, which is 0 to pi over 2. But then from here, for the sine, you'll notice for the sine and for the cosine, we can use complementary angle formula on that. And what that's going to do is flip the sines to cosines and the cosines to sines. So that's going to allow me to just rewrite this and clean up the angle. So when I do that, I have our same bounds, but now the sine here is going to become cosine. And then the exact same thing in the denominator, this sine is going to become a cosine squared of u, and this one's going to become a sine squared of u. But then what I'm going to do is just a variable change. So what we're going to do is we're going to change this all back to x, because I'm going to be trying to add it to my original integral. So we're going to now write this as cosine squared x, and then we'll get this back to sine squared x plus cosine squared x dx. And what I want to do briefly is let's go back to our original integral, and I'm just going to label this one as I. What I can do here is this is also going to be I, so we'll add those two together. And so let's see what we have. Okay, so now that I've added my original integral to this one here, now you notice that we actually have the same numerator and denominator. Now, of course, it's 1, so it's 1 over 1, and we didn't really need it anyway, but we also can do the cancellation, and notice that now our whole integral becomes 1. And so I'm just going to integrate this. We're going to have just x evaluated from 0 to pi over 2, but that's just going to give me pi over 2, because of course evaluating the 0 is just 0. And then to finish it off, I just need to divide this by 2 in order to isolate my original integral, so we'll divide by 2 on this side. And so for our final solution, we're going to get just pi over 4. Now, one quick note on this. You'll notice initially, going back to our initial problem here, I said that the King's principle is actually faster, even though I just did all those steps. So the reason I said King's principle is faster is if we just recognize that this whole integral is just going to become 1. If we recognize King's principle and we recognize the whole integral is 1, so we can just go right to the solution and like say it's going to be x from 0 to pi over 2. We get pi over 2, but we know it's 2 copies. And so we can basically go right to pi over 4. Anyway, just thought it was kind of a fun example of the King's principle, or something that you could have just done with regular trig identities. So I'll stop it there. Thanks everyone for watching. Have a great day.